Once you realize that life is constantly and always evolving, you basically turn on life and then you turn on this endless story. The universe is too big for my brain, but I'm really interested in the story of our planet. When did it start behaving like Earth? When did life itself start? When did the oceans form? When did the continents form? When did the first fish evolve? I mean, this is all heavy stuff for a paleobotanist, I want to tell you right now.
Hi, everyone. Today, I got to talk to Dr. Kirk Johnson. He is Sant Director at the Smithsonian Institution, National Museum of Natural History, which is home to one of the biggest natural history collections on the planet. He's also a paleobotanist and has hosted a bunch of NOVA documentaries like Polar Extremes and Making North America. I love this dude. We got into some really cool stuff, like how fossils form and where Earth's oceans actually come from. You know, stuff we all talk about right before bed. So, if you get as much of a kick out of this conversation as I did, I need you to do me a favor and rate us. Or you can leave us a review or drop us a comment and make sure you subscribe so you never miss an episode. Because we got more amazing stuff like this coming, and your support means everything. It helps us to reach more curious minds just like yours. So let's jump into the conversation. Kirk, welcome to Particles of Thought.
Hakeem, great to meet you.
Yeah, man. So listen, when I looked you up, I saw two words: geology and paleobotany. I hadn't heard paleobotany before, but when I think paleo, I don't think about the diet, I think about paleontology, which makes me think about dinosaurs. Tell me about paleobotany. I've never heard of paleobotany.
It's one of the obscure sciences for sure. It's fossil plants. And the reason I became a paleobotanist was when I was a kid, I loved finding stuff. Like I'd find coins and agates and rocks and fossils. And once you have a thing you can do as a kid, and you find that it works more than once, you do more of it. And I became like my childhood superpower was finding things.
Wow.
So I'd go on hikes with my dad. I'm like, what's this rock? What's that? Hey, here's a fossil. And when we're driving somewhere, I was like, Mom, can we stop here? I know some good stuff to find here.
Yeah.
So I started being like this search kid detective. And there were fossils around where I lived. And there was a fossil site about a 15-minute drive from my house that had cool things. It had fossil clams and snails, but there was also fossil wood. And then there was, I found a fossil walnut. And then I found a vertebrae from a dolphin. I'm like, what's going on?
Wait a minute, man. A fossil walnut?
Yeah.
So it looked like a walnut, but it was rock.
It was soft rock, but the shell was black and the meat was white. It looked like a walnut.
Yeah.
So I went to the museum in town, the Burke Museum in Seattle, and the guy said, yeah, there's a walnut specialist you can mail this thing to. A fossil walnut specialist. I'm like, okay. So I mailed to this guy, and he's like, hey, it's a walnut. You found a fossil walnut. And then, you know, the part of the porpoise, I found one porpoise vertebrae. It's like, where in the world do you find walnuts and porpoises together?
Right.
Well, at the edge of the sea where there's walnut trees and porpoises swimming. It's like a beachy deposit. And it was like 15 minutes from my house.
Sounds like you were set up to be a paleontologist like young, right out of high school. You didn't need to get a degree.
Like a paleobotanist even.
Paleobotanist, yeah. So what separates the fossilized plants from, I imagine everything doesn't get fossilized. Right? Yeah.
So here's the key thing that you have to know about fossils is that in order to become a fossil, you've got to die and you got to get buried.
Okay.
Right? And if you don't get buried, say you just fall over in the forest somewhere, you're going to rot away. So it's death plus burial. So if you're a dinosaur, you fall over and you die, chances are you're not going to become a fossil unless you live in a place where stuff gets buried. And what are those places? They're places like Louisiana, for instance. Right? Louisiana, the whole landscape is sinking slowly, and the stream is always dumping out sediment and putting more layers on it. So in an area that's sinking is what I call D world or deposition world.
Right.
And if you were to drill a hole beneath New Orleans, you would go down almost 20,000 feet in layered mud that's only 25 million years old.
What?
That's literally miles of thickness.
Yes.
It's miles. So if a fish died in New Orleans 10 million years ago, it would be 10,000 feet down
Wow.
And in the sediment it was buried in is being compacted into rock.
So I've seen this image of geologically of the Gulf of Mexico and how it goes out underwater, and there's like this big giant cliff.
Yep.
So all of that stuff is from the river?
Yeah.
Whoa.
Yeah, and from rivers dating back to millions of years. So the Earth is, as it erodes mountain ranges, all the sediment ground up mountain ranges end up at the edge of the continents and piling up in thick layers of sediment or limestone or other kinds of stuff. And that's where you create the fossils. An animal dies or animal plant dies, is buried in an area that's sinking, which buries it deeply, and that turns the sediment into rock.
Yes.
And they're at depth. And then eventually what happens is some other first phenomenon pushes that area back up. So areas that were depositional areas or D world become lifted up into what is called E world or erosion world. So if you can look at North America, for instance, most of North America right now is erosion world or E world.
It's getting eroded away.
There's mountains. Anytime you see a hill or a mountain, you know that stuff's eroding away. Look at the Mississippi River.
Anytime
drainage.
You see a river, right?
Yeah, exactly. In some areas, and so there are think about this. There are rivers in erosion world, like the Colorado River is cutting the Grand Canyon.
Yeah.
Not a good place to become a fossil. That's just grinding away and taking it out to the sea.
And it goes side to side and meanders.
But that same river, like Mississippi, when it gets down to New Orleans, great place to make a fossil. So that's the E world, D world difference. And the best place to find fossils, and like maybe the best place in the world to find fossils, is Western United States, because most of the last 500 million years, that landscape was sinking. It was D world. But then when the uplift of the Rocky Mountains started, it pushed that area back up and exposed those rocks in E world. So you want D world.
So you bury them, then lift them, and erode the stuff off the top of them, and now they're exposed.
Exactly. And sometimes you uplift them in an irregular way. So in one place, you might be able to see a cross section of the entire stack. And there's a place near Cody, Wyoming, where you can see from 2.5 billion years to 60 million years in one spot.
Jeez.
It's better than the Grand Canyon.
That is. And so because they've been lifted and turned now, it's more horizontal or at an angle rather than
exactly. It used to be flat and then it turned up and they're almost vertical, and you just count the pages like this all the way through.
Wow. And each layer has its representative fossils.
Exactly. There, like always, there's sort of local D world, like the immediate area around you. Like you're standing next to a mud bluff and it slumps down and buries you.
Right.
You just got buried in a little narrow piece of D world.
I see.
But if you want to look at it at the continental scale, most of North America is E world, but there are little local ponds and little local lakes. But those local things are not going to get preserved. They'll eventually fill up and erode away too. So the fossils are going to be in those places where the whole landscape is sinking.
Whole landscape. So what places would that be on Earth today?
The edges of the continents primarily, or the shallow, low elevation parts of the margins of the continents.
Okay, is that generally true throughout history?
Yeah. So as a result, we really don't have much of a fossil record for mountains or hills.
Wow. So for example, right now, humans are distributed primarily along coastlines. So would it be the case that land animals, even though it's geographically limited, it's still a good representation because that's where most life is going to concentrate anyway? Is that fair?
It's true. That's probably the case, but you're still going to miss the mountain goats and stuff like that, right? So
they still
it's
exist.
Things that live only at high elevations, or even on the Great Plains. Some of those things do get preserved, like the animals of the Great Plains are preserved because the Rocky Mountains came up and all the sediment coming off the Rocky Mountains shed and buried things under river sediments. And then that area is still coming up, so those river sediments are now being exposed. And so you have that kind of local D world is a source of good fossils on continents. And we found an amazing site in Colorado in 2012 that was a lake on top of a hill at 9,000 feet.
Whoa.
And it filled up with
Lake Tahoe. No.
No, it's at Snowmass Ski Area.
Snowmass.
It's right 700 yards from the base of the ski area. There's a little 12-acre lake that turned out to have been an Ice Age lake that filled up between 120,000 years ago and 50,000 years ago. And we found 50 mastodons and 12 mammoths in this one little lake in 70 days of digging. It was an amazing thing. But that was a little tiny lake on top of a hill that was a little temporary bit of D world.
Yeah.
And in the future, that'll erode away and go away. But we got it before it eroded away.
Wow.
Our timing was very good.
Good timing.
Yeah.
But over geological history, a lot of those have come and gone.
Yeah. Oh, yeah. Because that's at the top of the hill. It's going to go.
Right. It's going to
Hills go away. Mountains go away.
They're temporary.
Yeah. Never trust mountain ranges. They're undependable.
They
erode away.
All right. You can't depend on them.
Yeah.
Later, man, we're going to get back to this because one of the things that I feel like as science communicators we don't do quite often is we tell what the results are, but we don't tell how we get them.
Yep.
But we'll get to that. But what I want to go to first, man, is sort of like an ultimate fossil. A fossil from the foundation or the formation of our solar system. I hear you got an asteroid.
Well, we all share that asteroid. It's asteroid Bennu, which is, it's a 550 meter diameter blob of rocks. It's actually like a gravel pile that's all held together by loose gravitation. And NASA had the vision to send a little Osiris Rex out there to go take a look at this thing. And they got there and they orbited a whole bunch of times and made a geologic map of the surface of this thing.
Right.
And it's got boulders and pebbles and things. And then they had they moved the spaceship into position and punched a little sampler can the size of a tuna fish can into this thing. And it went way in further than they thought. They were like,
interesting.
When they got close, they were really scared because they saw all these huge boulders the size of buildings on it. And they're like, oh, what if we hit on a rock? But they landed it right where there's a spot and they just punched it in. And it was kind of like just loose gravel in the air. And they brought back, I think, 150 grams of samples that the spaceship then left Bennu, flew back over Earth. They dropped it out, it parachuted down, landed in the desert in Utah in this little capsule that was about this big around. And then they took off the lid of this thing, and here's like 150 grams that look just like granola, little pieces, little chunks of stuff. Yeah. And those samples are untouched by Earth's atmosphere.
So they're subsurface of the asteroid? So it's not, is it surface material, or did they actually because you said it went in deeper than anticipated.
Yeah, I think it went into maybe the length of my arm deeper. It wasn't a huge depth, but it was more than they expected. They expected a hard surface, but it was really just loose material, kind of loosely held together. Yeah. And so you have all these particles that they came back. And at the Smithsonian Natural History Museum where I work, we have Tim McCoy, who was on the Bennu team. So one of the very first samples, Tim was there when they opened the can. He got to bring home some samples, and we had acquired this great analytical device so we could actually look at these samples. And within minutes of these samples being in the building, it had it under the equipment. We were looking at this thing, and he's like, "Oh, there's hydrated minerals here. There's all this incredible stuff."
Wait a minute, hydrated?
Yeah,
water.
Yeah,
on a dry asteroid pile of gravel in the solar system.
So there you go. So water is the first thing you're looking at, and what's cool about rocks are that rocks are made up of minerals, and minerals are made up of various things, and some minerals have water in them.
That's what I was going to get at, right? There's a difference between water-bearing minerals, and there was liquid water here.
Yeah. But the water-bearing minerals has H2O in it.
Yeah, but it could be ice.
Or in the molecular structure of the mineral.
Molecular structure, right. Yeah.
So, but it's there. It's water. It's not. It wasn't a glass of water on the Bennu did not have glasses of water.
Well, here's what I'm getting at. Yeah. So a lot of asteroids are the remnants of protoplanets that collided and got broken apart. That's why we get chunks of iron out there, right?
Exactly.
Yeah. And so I can imagine that could it have been possible that one of those protoplanets actually had liquid water, and somehow that got incorporated into Bennu? Or is it just the everyday kind of space water?
So this was the big surprise on Bennu, is that the first glimpse is like, wow, we've got these minerals, we've got hydrated minerals. Other researchers in other labs like, hey, we're getting some amino acids out of this stuff. Whoa. But what our team discovered, which was so amazing, was they're museum-based researchers. So we have this amazing collection of the world's minerals, and there's thousands of different kinds of minerals on planet Earth, and a lot of those minerals were formed in conditions that formed on planet Earth. Some of them are mediated by life. For instance, there's minerals that are deposited by living organisms like shells and clams and things like that, or humans and our bones. Those are minerals, right? So life creates minerals. So Earth has a high diversity of minerals because it has life. Yeah. So there's it used to be that whole animal, mineral, vegetable kind of thing.
Right. Yeah.
That's a little bit touchy more now complex. Because animals have minerals.
Yeah. So they're let me wrap myself in rock, then you can't eat me.
Exactly. And some things do that, like turtles and things like that. So as they were inspecting these grains, literally micron by micron with their instruments and analyzing the grains, they started noticing some minerals that were familiar to them. They're like, I've seen this mineral somewhere before. And what they were finding evaporite minerals. And these are the kind of minerals that form when you take a lake in a very warm area and you evaporate the water, like the Dead Sea or the Death Valley, where there's a lot of sun, it's very hot, and the river's coming out of the mountains carrying minerals, and then it evaporates and leaves those minerals behind. And think about the borax trains of California.
Right, yeah.
There's a whole sequence of minerals that formed in Death Valley. As the water comes off of the Sierra Nevada, it evaporates, more water goes back. You get a series of different evaporite minerals. And they started finding these minerals in the Bennu sample.
So is it that they come in a particular combination? So it's sort of like a signature of this
Yeah, there's an evaporative series. Like you evaporate off one kind of mineral that leaves a different composition of the water. The next time you evaporate, you get a different mineral. So it's actually an evaporative sequence. And they start finding the evaporative sequence, which means that, Bennu was probably rubble from some exploded planet. But on that planet, there had to be a sequence where water was evaporating and creating evaporative minerals.
So that means a collection of liquid water.
So you got water now, you have all these different minerals, you have the amino acids and something like all the things you need to make life are right there.
Man, that's amazing. Because, one of the ideas that I've seen about life, where it might be found. So we typically look at planets and moons, but there's this one scientist who said comets. If you have some radioactive nuclides inside the comet, that could create enough heat to melt the ice and create little water reservoirs. But this is very different because you have water that's liquid, then it dries. Then it's liquid, then it dries. Then it's liquid, then it dries.
Now you think about Bennu, it's like it's out there and it's exploded from somewhere, which means that, and it's from the beginning of our solar system.
What's the age? Did it get an age on it?
Well, I don't know. It's probably 4.567 billion, more or less the age of our solar system.
Right.
So you've basically got debris out in the solar system on an asteroid sitting out there. That's a signal of what was in the solar system when the solar system founded, which means that at the beginning of our solar system, even before Earth cooled, you've got evidence for the conditions for life before you have Earth, because Earth, remember, it was a molten ball, and then it got hit by the body that became the moon. So the moon, the Earth's a bad place to be for its first 100 or 200 million years, right? You start to enjoy life, things are cooling down, then bam, you get this thing, and then the moon forms. So the rest of the solar system maybe has a 200 million year head start on the Earth. So you've got conditions that could maybe form life somewhere else. Out there. And then how does life get onto Earth? Well, maybe some of that stuff that was blown from somewhere else lands on Earth. And you start the process.
Wow. So not necessarily from out. So essentially, what this suggests potentially is that you don't even need fully formed planets to get life. You can, at the protoplanet stage, you can have water. You're doing this complex chemistry that results in amino acids. So
what's to stop you?
So my understanding of, this is a good question for you. So we look at the origin of life and the origin of the oceans. Right? So what are the theories of where the oceans originated? How did we get them?
So you don't have many options, right? Because right now you've got the planet where 70% of it's covered by salt water. And it's even an amazing question to ask or imagine what the Earth didn't have oceans, right?
Amazing.
But you got to figure if it started out as a molten thing, there was no ocean there then. It's a giant blob of molten rock.
It would have boiled away, right?
So you have that problem. And Earth's a big thing too. Like it's got a big diameter, it's got a lot of volume. So you got to ask yourself what's in the middle of that, and how does the structure of the Earth itself form? How does its core and its mantle and its crust form? Where do the continents come from? And where does the ocean come from? These are like fundamental questions about how our Earth became this amazing place it is today, with lovely oceans and great mountain ranges and all that kind of stuff. So, as you pointed out, one idea is you have this molten blob, it cools down, and then it gets hit by a bunch of comets, which deliver truckloads of water, because the comet's got a lot of ice, and so the comet, it delivers the water. And there's ways to test that. I don't really know how rigorous those tests are, but the other option, really the only other option, is the water was already there in the rock of the planet, and it was in hydrated minerals that then somehow outgassed, and the water started to accumulate on the surface. And the question there is, how do you keep the water on the planet. Like what holds the atmosphere and the oceans to the planet? Obviously, there's gravity, but so you basically have either it was delivered or it was already there. Those are your two options.
So I guess the question is, if you have a situation like Mars, where the atmosphere is incredibly thin because it's been eroded by solar radiation.
Yep.
So Earth's atmosphere doesn't erode as quickly. My understanding from Jim Green, who's who was the chief scientist at NASA, is that it's being eroded, but geologically it's being replaced as rapidly as it's being eroded away, right? But the magnetic field of Earth slows down the erosion of our atmosphere. Do we know how early our magnetic field kicked on, the Earth's magnetic field?
I certainly don't know the answer to that question.
Okay, yeah.
But I mean, that's you're basically asking all the right questions, which is when does Earth start acting like Earth? This is all heavy stuff for a paleobotanist, I want to tell you right now.
Right? Oh my goodness. Well, I would imagine it's all mixed together, right? So you got the planet's evolution and life's evolution. So it's almost like life becomes its own geological process that works together with the planet.
Absolutely. And once you realize that life is constantly and always evolving, you basically turn on life, and then you turn on this endless story that we're part of right now. What things are, and what's so cool, I think what I kind of there's so much cool stuff here that I kind of restrict my knowledge to the planet, because I'm like, the universe is too big for my brain. But I'm really interested in the story of our planet. How did it start? How did the pieces come together? When did it start behaving like Earth? When did life itself start? When did the oceans form? When did the continents form? When did the first forests form? When did the first fish evolve? I mean, in every one of those things, it's got its own tale. But if you put it in the context, we've got 4.5 billion years to tell the story. And then you just start chipping away at every aspect of the story.
Well, let's go back to that Earth without water sort of image, because we do have continents. So if you had an Earth without water, so I imagine that the ocean is deep. So do you imagine a world that's pretty much, if you look at other bodies that don't have water on them, they appear to be more or less smooth if you get rid of the cratering. It's not like these giant, you have the places with volcanism like the Mars and Venus that have giant volcanoes. But other than that, you don't have like big basins and then huge continents sticking up. Is that what we imagine?
Well, think about what you just said, because when you say the ocean's deep, it's only 36,000 feet deep at its deepest point. Most of the oceans maybe only 8,000 feet deep. That's only a mile and a half deep.
That's pretty damn deep if you ask me.
Well, compared to the size of the Earth, it's nothing. I'm like, if you looked at the Earth, if you drained all the water off the planet right now, your highest point's Mount Everest, your lowest point's the Marianas Trench. What's that, 29,000 feet and 36,000 feet? So like 60,000 feet, what's that, 10 miles only? So that would, from space, Earth would look like a polished bowling ball. And so there's really no topography there to speak of at the scale of the planet. And then you have to ask yourself, well, how do you get that topography anyway? How did you get the deeps in the ocean, and how do you get the highs of the mountains? That all happens because we have plate tectonics, and the continents are moving, and the plates are colliding with each other. And these deep part of the oceans are where two oceanic plates come together and make a deep subduction zone. So the trenches are
trenches are subduction zones.
Those are plate-to-plate collisions. And when you get a continent colliding in a continent, like India hits Asia, you get the Himalayas. That's where you get your high points. So you can't even have topography we have until you turn on plate tectonics. And then you think about plate tectonics, that's ocean crust and continental crust. It's like, what came first, chicken or the egg? Continents or the ocean?
Right. Do they form together? There. And I guess another question is does the weight of the water sort of segregate the continents from the oceanic crust? I'm just swagging here, scientific wild-ass guesses.
Well, the thing about it is water weighs a lot less than rocks, and different rocks have different relative densities and masses. So you have a heavy rock and a light rock. The light rock's going to float on the heavy rock. Right. So you have, and also rocks themselves. We think of rocks as really hard things you throw out windows.
Right.
But the reality is that rocks are like the products of any other cooked item. Right. They start out. Some of them start out liquid and they cool to hard rock. Some of them start out as sand, which cements, become sandstone.
Man, you're triggering me. I remember elementary school, we had to learn metamorphic, igneous, sedimentary. I don't remember what's what anymore.
I'll tell you using a food analogy. How about that?
Yeah.
The simplest one is sedimentary. Those are just like particles of sediments, sand grains and things. So the food analogy there is salad. It's just a bunch of stuff thrown in a bowl.
Got it.
Whatever is coming downhill, it's just a bunch of stuff. That's salad.
Is it always in association with water?
No, it can be blowing in wind too.
Oh, okay.
Yeah, wind dunes, sand dunes, for instance. So water or wind, both. And you have Mars, you have dunes.
Oh, they have sedimentary.
They have wind, right? Right?
Yeah.
So and there's also on Mars evidence of waterborne sedimentary rocks. So you have both kinds. Then there's the igneous rocks, which are the rocks that start out their life melted, right? Yeah. And the food analogy there is a fondue. You melt your cheese.
All right.
Melt your cheese. It's a molted thing, and it cools to a blob, and you eat it when it's a little bit harder, but whatever. So that's it. And then the tricky one is the third kind, the metamorphic rocks. These are rocks that got heated and squeezed, but they didn't melt. They didn't go all the way back to being fondue, but they were heated and pressed enough that their crystal structure and even its content changed. And so the food analogy for a metamorphic rock is a lasagna. You start out with, your noodles and your sauce and your burger and all that stuff, and then you cook it, and it changes a bit. You can recognize it a little bit, but since we only cook lasagna to a certain temperature, you only get lasagna that looks like that. If we cranked up the temperature on lasagna, it might have a different form even still.
Right.
So all three states can turn into the other state depending on what happens to them. And this is why we don't have the oldest rocks on planet Earth, because the Earth is always baking itself, melting itself, and grinding itself up.
Wow.
It's like its own factory that's churning away and cranking away on that thing. The other piece is that we have a lot of unique minerals on planet Earth because they're formed by interactions with living organisms.
Right. Yeah,
right,
my mind went there as you were saying that life must play a role also.
Yeah, and this took surprisingly long to figure out for people, but like this whole idea that there are lots of minerals that wouldn't exist if they didn't have some living organism that was mediating the formation of those minerals. The study of the earliest life forms really only got going in the 1950s when they started looking at Precambrian rocks and slicing them open and finding little things that look like cells or little filaments and things. So much of what we know has been accrued in about the time that you and I have been alive.
Wow.
I mean, the understanding of our planet is leaping forward in great bounds all the time, but so much of it, if we'd had this conversation when we were 5 years old, there's a whole bunch of stuff that we wouldn't have known collectively, right? That's the thing that always blows me away is depends on when you stop paying attention to science. Don't do that because science moves forward so fast every day. Every day.
It absolutely does. This podcast is from the producers of Nova. Nova is supported by Carlisle Companies, a manufacturer of innovative building envelope systems. With buildings responsible for over a third of total energy use and energy demand on the rise, Carlisle's mission is to meet the challenge head on. Carlisle's energy-efficient solutions are built to reduce strain on the grid. For example, Carlisle's Ultra Touch denim insulation, made from sustainable recycled cotton fibers, delivers high thermal performance for improved energy efficiency while being safe to handle and easy to install. Made from 80% recycled denim, Ultra Touch diverts nearly 20 million pounds of textile waste from landfills each year. Operating nearly 100 manufacturing facilities across North America, Carlisle is working towards a more sustainable future. Learn more at carlisle.com. So you've been chasing these fossils since you were a kid. Where has that taken you on the planet? And tell me some of the coolest surprises that you've encountered.
So I have found about 1,000 fossil localities in my time on all continents. And my favorite continent is North America because I'm from North America, but because the western part of North America, the Rocky Mountain region, was for a very long period of time primarily D-world. So it accumulated layers and layers and layers from the Cambrian all the way up to the present, almost the present.
So let's define the Cambrian for those who might not know.
So the Cambrian period starts at 542 million years ago. And that sort of starts the, it's not the very beginning of big life forms, but it's sort of much the starting gun for the evolution event. It's the first time you see actual animal fossils, for instance, is the very bottom of the Cambrian, so 542 million.
And so at this time, is it 100% in the oceans?
Well, there's land. It's just there's not.
Life.
Yeah. It's not clear what's on land. There's land, but it's not clear if there's anything living on land at all. That's one of the unanswered questions.
I see.
There's probably some kind of microscopic microbes on land, but hard to know. But it predates certainly any plants or anything on land. So then you go through this sequence where you eventually evolve a diverse ecosystem in the oceans, and then you see land start to be populated by some very early land plants and some very early land animals, but again, probably little insect-like or spider-like things and little tiny plants that might be only 3 inches tall or 2 inches tall.
Right.
And then eventually you start to get bigger plants and the first forests.
So wait, one of the things I saw on YouTube,
of course,
that I discovered were these big giant fungus things.
So it's a fossil known as Prototaxites.
Okay, that's a mouthful.
It is like most fossil names are mouthfuls. I'm going easy on you.
It's not like
here.
in my field of astrophysics, black hole.
No. we got some good names for you. So this Prototaxites, very weird, enigmatic, because looks like it's a fungus of some sort. And they are these big trunk-like chunks. And that's all you get. And then you can look at this in cross-section and you slice them up and look in cross-section. And you can see things that kind of look like fungal threads and fungal hyphae.
Oh, interesting.
But they're way bigger than anything else around there. And when they first appeared, how big they got and what they actually related to is pretty much at the hairy edge of what we know. Because they're only known from a few places in the world. And how big they got, well, there's a couple that look like they might have been pretty big. So you see reconstructions of them, but that's just somebody saying, well, I'm going to paint some big thing that looks like a big thing. So a lot of debates on this stuff. And so much of early life is like that. We have fragments of these things. And you have preservation that doesn't show all the details. And it's sort of like, it's likely that they're fungi. They might be something else, but who knows what else it would be.
They could be neither plant nor fungi. It could be something different potentially.
But they're organic, they're not an animal. So you're kind of like in a realm of the things that we know about, fungi seem to be a reasonable interpretation. And I think the further back you go in time, the blurrier the view is. And there's plenty of things in the fossil record where we know we've seen this thing before, we've given it a name. We don't know where it fits on the tree of life.
So here's the question then. If you're a paleobotanist, are there paleofungusists?
There are.
Wow.
So there's paleo anything you want, because any living thing has its fossil story. And I think it was science. Like we all specialize, and I became a paleobotanist because you got to get a PhD in something. But I love the whole story.
The whole story of ancient life, ancient Earth.
And everything's in context. So paleobotany is in the context of where were the first plants.
And
then when were the first forests, and then when were the first leaves and the first seeds and the first walnuts.
So is there a case of plants becoming, is it something that happened a single time and spread out, or is it something that just kept popping up and then was able to survive?
It's a hard question to answer because, but one thing is very clear and important thing to realize is that it looks like, because of the presence of DNA, that all life forms are related to each other. They all have DNA. And so when you start to evolve a complex life form, no matter what it is, it's got its own DNA. It still implies it's related to the other things that formed. And the further you go down the evolutionary tree, the less likely it is you're going to reproduce the same thing, because it's had its pathway that you've already gone down.
So the new stuff takes the blueprint from the older stuff and builds on that.
But
a lot of the old stuff is still here, right?
It's true, but then this is why we're so worried about extinction, because let's take, for instance, a bison. If a bison goes extinct, we're kind of done, because you can't re-evolve a bison. You can't go back to the start.
Yeah,
the extinction is when you lose that whole lineage.
Yeah, it's a whole process that you've lost.
Yeah, right. And it's like, its genealogy goes back all the way back to those first DNA molecules back in the ocean. So, and the fossil record is full of things where you lose things, like the big dinosaurs, like the long-necked dinosaurs.
Yeah.
They're not just going to pop up one day again. We had them, they're gone.
They're gone.
Right, and that's the cruel thing of evolution and extinction is things are the ends of lineages. So when you lose them for whatever reason, they're not coming back.
So what do we represent then? All life forms today. So I read somewhere that something like 99% or higher of all life species are no longer here.
Yeah.
But then I think, what does that really mean? That doesn't mean they necessarily, like there's extinction that comes from, birds are still here, but yet they are dinosaurs. And we say dinosaurs are extinct. So you evolved to something new. You didn't die off. So it's not the end of the lineage. So when you say that sort of phrase that 99% of all species are gone, does that mean that, what percentage of them evolved into something else and what percentage of them just died off?
Again, hard to say because we have no idea how many things were alive at any point in the past because the fossil record is so incomplete.
Right.
Right. So you don't really know. And your point's well taken. Certain things do have descendants, but you can destroy entire lineages. So for instance, if the birds go extinct, then dinosaurs will be truly extinct. Right.
Right.
And birds were just one branch of dinosaurs. So all the other branches of dinosaurs went extinct. Except for the bird branch. So, and there were some really cool dinosaurs. I mean, there's this thing called Paleobotanist that is 100 feet long and its head's 60 feet above the ground and its one leg bone is taller than I am.
Man, it is so hard for me to imagine. I step into the museums like yours and I see these giant animals and I just cannot envision that thing walking around, right? It's hard enough when you see an elephant lumbering along, right? Something many times the size of an elephant, like the mechanics of that, are they fast moving? Because they were warm-blooded, right?
The big ones, who knows? Maybe not. I mean, this is like a good theory. Some of the more bird-like dinosaurs almost surely were warm-blooded, but the big ones, they're big animals, and there are all sorts of mysteries about those animals. And I will say that were it not for fossils, we'd never have an idea that those animals existed, first of all. And when you see them in museums, like, I can't believe that thing existed. But I'll tell you what, when you are digging and you find one of those things, that's where your brain gets wrung hard because you dig out a 7-foot-long femur. And you know that you dug it out. There's zero doubt in your mind that was a living animal. And those long-necked, long-tailed dinosaurs, the sauropods, they were around on planet Earth for like 150 million years. Humans are 300,000 years.
Jeez,
So here's a kind of animal and they're found on all continents. There was a very successful kind of animal. So even if we can't imagine how they walked, they walked. They walked.
150 million years of lineage.
Okay,
so I've studied human history a bit, and one of the things that is mind-blowing to me is during Homo erectus' time of 2 million years, brain volume went from like 600 cc's to 1,200. It doubled, right? In 2 million years. So now you're talking about something, a lineage that's 150 million years. The difference before the before state and just before the meteorite hit, like what were the major changes that happened? Was it just the evolution into small mammals and different reptiles, or did some of them become smart? Like what?
So here's the thing that's so incredible is that the state of the planet does change from time to time. Like the planet is in orbit around the sun. It's got the moon. The moon gives us its months. The Earth, its rotation around the sun gives us our seasons. We have these things that are there, but certain things have changed. Like the Earth is slowing down in its rate of rotation, for example. So there used to be 480 days per year.
Wow.
Now there's only 365 days per year.
Because so as the Earth is orbiting the sun, it's spinning, so it would get 480 spins in by the time it made one complete orbit.
Right. So the days are a little bit shorter. And so things like that happen. Or we get a little bit closer to the sun, so the climate's a little bit warmer, or a little bit further away.
What is it, the Milankovitch cycles or something like that?
Yeah, and those are pretty, like those happen on these sort of 20,000, 40,000, 100,000 year cycles. And if nothing else was changing at all on the planet, if just the Milankovitch, you'd have this cool, warm, tick-tock thing going back and forth on these cycles. And that's what's driving things like the most recent glacial periods, the advances and retreats of the big ice sheet that covered North America, for instance.
Yeah.
And today, we sit here and enjoying our weather in Boston and Seattle and New York. But if we were here 20,000 years ago, there was 3,000 feet of ice on top of Seattle, New York, and Boston. 3,000 feet.
Wow.
That's 6 Space Needles. And that was only 20,000 years ago.
That's like more than half a mile. Ice.
Yeah, on top of what we call cities today.
Yeah.
So there are processes that are happening over time. And when you shift a major process for whatever reason, that then challenges the life forms to respond.
Right.
But those long-necked dinosaurs, which first appear, sometime in the Jurassic period, maybe 180 million years, they kind of disappear at the asteroid impact at 66 million years. They've got well over 100 plus million years of time. They were living in a time when there were no polar ice caps.
The entire 100 million years or so.
Yeah, there was some times where it cooled down a little bit, but the evidence for polar ice caps there is very sparse, which means that, and I see the world of the last 400 million years, I see the world as a view between the battle between trees and ice. Because when there's lots of ice, there's not so many trees. When the ice retreats, there's more trees.
I see.
So, and today, for instance, Antarctica is covered by 10,000 feet of ice. And Greenland, the same.
Yeah.
Dial the clock back 50 million years. Antarctica was completely forested. Greenland was completely forested. There were no ice caps on the planet. So you have a tree world versus an ice world. So
how many years ago was that?
Well, 56 million years ago was a high peak. 100 million years was even a higher peak of temperature. But remember, dinosaurs first appear in the geologic record around 230 million years ago. And they disappear at 66 million years, except for the birds.
Right.
That one lineage that survived. So you have this nice long chunk of time where dinosaurs, these long-necked dinosaurs, they survived. That lineage had a long time, but it lived in a world that wasn't all that different. It was a forested world.
Yeah.
And to become a big herbivore, what do you need? You need like endless salad.
So, Mr. Paleobotanist.
Now we come back to it.
Were trees hella big to feed all these big dinosaurs? Or is it a different forest world than the forest worlds we have today, than like the Amazon or the Congo?
So now you're talking my language here.
All right.
We've gotten rid of all this earlier stuff. Now we're on to the plants. But the thing is that think about trees. People don't think about trees very much at all. I mean, I find that people they love animals and they just ignore plants. And there's gardeners, of course, that like growing plants.
Wait a minute, man. Let's get back to my Mississippi upbringing. So one of the things I used to be proud of that I can't do anymore was, the ability to identify trees by their bark and leaves. Like, because, we haul pulp wood and, you had to get this for firewood and, you ate this or that. So you knew you're a forest. Today, I lost it all. Yeah.
And if you go to Mississippi, there's a nice diversity of trees. If you went out and walked in the forest and if you're walking in the swampy areas, a lot of bald cypress and sweet gum and sour gum and that kind of stuff. But if you go to the Amazon today, you walk in 1 acre of forest, you might have 200 or 300 species of trees.
Wow.
Like Mississippi might have 20 or 30.
Wow.
Amazon might have 200 or 300. It's just an interesting thing. It's like we ask now the question, when did the first tropical rainforests form?
Okay.
When did the first pine forests form? When did the first redwood forests form? Because there's different kinds of plants. On planet Earth today, there's about 400,000 different species of plants.
Okay.
Now about that, maybe 100,000 different species of trees.
Okay.
All right. So there's a lot of different kinds of trees. And trees are very interesting because the different kinds of trees have long lineages. So there's a thing known as the ginkgo tree. We have ginkgo fossils that go back 180 million years.
Wow.
So the ginkgo trees were alive with the dinosaurs. So there actually are some kinds of trees that are alive today that were alive with those dinosaurs. And this is the kind of cool thing is that the planet's always changing, but some of the cast members in the play
Yeah.
have long roles.
How long can a seed last? Like I can imagine that if there's some big disaster, you know, seeds can, even if all the trees get burned up, you know, the seeds may survive for some. Like, what's the longest?
There's some examples of very old seeds from like archaeological sites that have germinated. So thousands of years, maybe in some rare cases.
Oh, wow. So that gives you enough time.
Yeah, if you preserve the seed. And we have
yeah.
these seeds that were frozen in a seed bank in the Svalbard and
Right,
the
right.
Arctic Islands now, where we're like freezing seeds to preserve them from the future. So depending on what kind of seed it is, it can last a while. I would be pretty surprised to see an Ice Age seed germinate.
Okay.
But I'm not going to say it's not going to happen. I'm just going to say I'd be surprised. If it was frozen at the time, maybe it comes back. But trees, there's so many things to say about trees that I'm going to...
Well, you are botanists is in your educational heritage, so...
Yeah, I mean, I think my point is that most people just don't pay attention to trees, and they have so much to tell you because trees have growth rings. So you can cut them down and tell how old they are. Some trees are... You know, the typical age of a tree is about the same age as a person. A typical tree lasts about 60 or 70 years, but some kinds of trees last thousands of years. Like the bristlecone pines go back like 4,000 years. Yeah. So they're good at telling time. They're good at telling time in human kind of stories, and we often use trees with growth rings to tell us about archaeological sites because there's that thing known as dendrochronology, or using tree rings to measure time. It's one of the many ways we measure time back in the past. Yeah. But if you go to the tropical rainforest and cut a tree down, it has no rings.
What?
Yeah, because there's no seasons.
Oh.
A ring is when the tree grows slowly in the winter. So it's like tree rings are something that's very familiar if you live in a temperate region. But if you go to the tropics and you saw a tree down, it's like, looks like butter.
It's ringless.
Yeah.
Yeah.
And so in the tropics, if you want to measure how old a tree is, you can't count the rings. You have to watch it grow.
So to know the growth rate. So
you measure it every year and see how back it's growing. So we have Smithsonian has a plot in Panama called the Smithsonian Tropical Research Institute. And we have this place called Barro, Colorado Island, which is 50 hectares, where they've measured every single tree every 5 years for the last 50 years.
Well, here's the question, though. Are those trees the human lifespan type trees, or do they live much longer? Because if they live much longer, you would imagine that it would have to undergo different environmental conditions, which would increase or decrease the growth rate, right?
Exactly. So what we're finding is that in tropical rainforests, it looks like the average tree lasts about as long as a human, 70 or 80 years. Because trees get diseases, too.
Yeah.
They get knocked over by windstorms.
Yeah.
They get burnt by forest fires.
Wait a minute, let's talk disease. So I can imagine fungal.
Yep.
I can even imagine bacterial.
Yep.
Do they get viruses? Like, can a tree catch a cold?
I should know that, but I don't.
I love that about you, though, man. I feel like one of the best answers a scientist can ever give is I don't know. Because to me, the hallmark of when you cross the threshold of being a scientist is when you know the difference between I know and I don't know.
Yeah. And even know is a little bit of a stretch because I think I know.
Well, I know with some uncertainty. Right, there's going to be an error bar on my no.
Exactly. Exactly. But that's why you got to keep reading, right? You keep studying, you keep watching what's happening because the world. There's so many scientists. There's now 10 million scientists on the planet.
Thank you for that.
Isn't that cool?
That is amazing. I had no idea because what I tell people is what I've been telling people is that when you look at scientific knowledge. It's not like the good old days where you had like this one lone person. Every country has armies of scientists. And now 10 million people. I never had a number to attach to that.
No, it's interesting because I believe there's 8 billion people. So what? Scientists are 1 in 1,000.
That's a lot higher than I would have imagined.
Yeah, it's like
1 in 1,000 is a
Is that right? Did you do my math right?
I don't know. 8 billion is
million.
10 to the 9. And 10 million is 10 to the 7.
Yep.
So it's it's 1 in 100.
Can't be.
So we're going to turn 8 billion into 10 billion.
Yep.
And so now we're at 10 to the 10 compared to 10 to the 7.
There we go. 1 in 1,000.
1 in 1,000.
All right.
Well, let me ask you this other question then. The fossilization process. So, I've been to the Painted Desert in Arizona with all the fossilized trees. And they're rock. So pretty much fossil equals not organic stuff in its current composition. It's minerals, right? Is that always the case, or do you actually get some organic bits here and there?
So I would define fossils different. What you've described is a petrified fossil, where the fossil has been turned into rock.
Yeah.
That's one type of fossil.
Okay.
A fossil is basically anything old. It's a very
right?
It's
broad.
It's very broad because we have fossils that are almost unaltered entirely. I can show you, for instance, a site that we worked up in the Canadian Arctic Islands that was 5 million years old, and the wood looked like driftwood off a beach.
So it's still wood.
It's just wood. It just happens to be 5 million years old.
Wow.
I have a site in North Dakota that I dig called ginkgo salad. And the reason we call it ginkgo salad is when you crack the rock open, this is 67 million year old rock, the ginkgo leaf peels off the rock. It's a leaf.
What?
You can eat it.
It's like the pressed leaf in your...
It is.
But it's encased in rock.
Yeah.
Wow.
Right? So, and petrified wood is wood that's been invaded by silica-rich water. So it turns the wood, or the wood is replaced with glass effectively. But that also happens. I have places where fence posts are petrified because of the groundwater flowing has silica or calcium carbonate in it. And you can actually take a chunk of petrified wood in some cases and put it in hydrofluoric acid, which is an acid that dissolves silica. It dissolves glass. So don't put hydrofluoric acid in a glass jar because it will dissolve.
Wait, HF?
Yeah, HF.
Oh, man.
Nasty stuff.
Nasty stuff. I used to work in the semiconductor
field,
and then we had to watch these horrible videos of HF accidents.
It kills people.
Yeah.
So you take a piece of petrified wood and you put it in hydrofluoric acid. It will dissolve the silica out and give you the wood back.
Wow.
The wood structure is still there.
So we're talking like tens of millions of years old.
Could be less. I mean,
I'm saying up to, right? Could that work with something?
Oh,
that's
yeah.
Like,
yeah. Man. I mean, there are plenty of fossils from 400 million years old where you can dissolve away the rock and get the organic material. Like the coal seams of West Virginia, there are these things called coal balls, which are concretions made up of calcium carbonate that formed around these plant parts. What you do is you saw them in half, you dip the flat surface in a light acid, which etches away the calcium carbonate, and then you lay a little bit of acetone on there and put a sheet of acetate and peel it off, and you can get a peel of the cell structure of the plant.
Wow, and look at it under a microscope.
Yeah,
and
you
see
can
the
cell by
cells.
cell. And that's 400-year-old plant.
400 million?
400 million, sorry.
Wow.
40 million. So this is now you're starting to get the joy of paleobotany.
Yeah,
here,
this is dope, man. This is dope.
Yeah.
So you said something, and this is something I've always wondered. I see these videos. They're walking in a stream or they're out in some place where there's all these big rocks, and they're like, and they grab a rock, hit it with a hammer, open it up, and there's a fossil right there. I'm like, how do you know? How do you know that rock had a fossil in it? And then what is the rate? Like you've been doing this a long time. You're probably good at it. Like, is it 1 out of 10? Like, how does this work, man? We want the secret. I want to find fossils in my backyard.
Perfect. There's several secrets here. One is you don't find anything unless you look for it. So that's a pretty obvious thing. And so certain kinds of fossils are in the rock, and fossil leaves are in the rock. And if the rock erodes away, it just erodes away the fossil. Because you think about it, here's how a fossil leaf gets formed. Leaf is on a tree. Leaf falls off the tree into the stream. Leaf gets buried by sand at the bottom of the stream. It's in a D-world situation. So the stream gets buried by more streams. After a while, that layer is so deep it becomes a hard sedimentary rock. Then later on, that area is uplifted. Now that rock's exposed to the surface. That leaf is in the rock. So I go walking along with my pickaxe, and I'm digging holes. I'll split a chunk of rock and crack it open. And I do this when I'm hunting for fossils. I might do that 100, 1,000 times a day. Just look, crack a rock, nothing.
But you have some sort of criteria to determine which rock you're gonna crack open, right?
I do, but sometimes when I have like young interns, I say just go dig holes, because sometimes my criteria locks me into missing things.
I
right?
see.
Like I think I know where things are.
Right.
And I think I do.
Yeah.
But I don't know what I don't know, as always.
Right.
And so I sometimes have the uneducated people digging holes too.
Yeah.
And sometimes they find amazing sites by random. And I'm like,
Right.
oh, I can find fossils there too.
Yeah.
But say you crack the rock open, and remember, there was a leaf that was there, but the leaf is usually rotted away, leaving a leaf-shaped hole in the rock, which means when you hit the rock with a hammer, it wants to open up there because that's a plane of weakness. So it's predisposed to open up where the fossil is.
I see.
So when you crack a rock and there's a leaf, or even a fragment of leaf, you're like, okay, now remember this. Leaves are like potato chips. You don't just get one.
Oh.
Right? It came off a tree.
Yeah.
A typical tree has hundreds of thousands of leaves. And I know this because I once cut down a tree and counted the leaves.
Man, you are committed to the art.
I wanted to know.
I
wanted to know.
Hey, you know what? I believe it now because you know what I did? You know, I have a bunch of trees. I'm kind of in a country place. And so I bought one of these extendo automatic cut the limbs off because they're growing into the areas they shouldn't. And man, when it came time to get all that stuff and put it in bags, I was thinking, they got to be 100,000 leaves on this tree.
Not a bad guess. Here's I had this thought. I said, I want to do this because I really just want to know. And I selected a 50-foot tall red maple tree that was about this big around at the base.
Yeah.
And I sawed it down with a buddy of mine, and then we cut off all the branches and stacked them all up. And then we sat down and we had a counting system where we had a pile of sticks, and every time you counted 100 leaves, you put a stick in the pile, so you wouldn't lose count.
Yeah.
And we took 18 hours, and we counted leaves for 18 hours, and this tree had 99,284 leaves on it. So your 100,000 leaf was a good guess.
Well, I just said that because you already said it. But you
I planted that.
You planted that, right?
Okay.
You led the witness. It reminds me of that thing where they show up with the jelly beans. They're like, guess how many jelly beans are in the jar? So you did that for a tree, and you got the
exactly.
number.
So that was just one tree, but it was the average tree in this forest. I'd measured all the trees in the forest. I'm gonna hit the average tree.
Well, let me tell you, a physicist would never do it that way. There's two ways we would do it.
Okay.
One way is either we would chop off all the leaves, put them in a big pile and weigh it, and then weigh one leaf. Divide it. Or the other way is we'll say let me take a meter by meter by meter volume, count the number of leaves in there, and then estimate the volume of the entire canopy.
Well, you know what I had done actually before then was because leaves all in the Northeast, all the leaves fall off in the fall.
Okay.
Right? They all fall in the fall. So I had gone to that same forest where there was leaf litter in November. So all the leaves were off the tree, and I had measured 1 meter square and counted the leaves in 1 meter square. And I divided that by the number of trees in the area. And I'd come up with an estimate of 103,000 leaves.
So close, see?
Yeah. So there's more than one way to skin a cat.
Or
count leaves on the tree.
Right, yeah.
But so now whenever I look at a tree, I'm like, that's a 1 million leaf tree. Or there's a 600,000 leaf tree.
Wow.
There's a 100,000 leaf tree. But my point is when you're looking for
you
fossils.
You have an intuition about it now.
Well, yeah, I mean, it's a useless intuition. Who cares about how many leaves are on a tree?
You don't know, man. That might save your life someday. You know, you're out in if only we had a tree with 200,000 leaves.
There it is.
There it is.
So, but get back to the fossil.
Gilligan wish he could have known that.
Yeah. Remember the professor?
Yeah, the professor. Of course.
So, when you're digging fossil leaves, it's rare that a leaf is going to be there by itself because it came off a tree that had 100,000 leaves. So, if you find one leaf, you're going to find more.
Yeah.
So when I find a single leaf, then I stop, I get the other tools out, and I dig a hole. And almost always when I find one leaf, I can find hundreds of leaves.
So what you're telling me then is that the material doesn't move far over these long time periods.
Well, yeah, I mean, and so I've done a lot of work in modern forests and asking the question, what happens to the leaves when they fall off the tree?
Yeah.
Like, what happens to the leaf litter?
Yeah.
And in leaf litter in a forest, it rots away by the next year because it's gone by the time the next year. But if that forest floor was flooded by a stream, you bury those leaves. So, and then the question is, how much does the leaf litter of the forest floor reflect what's actually in the forest? Can you take fossil leaf litter and make a description of the forest? So all those are like tools we use now when we're building ancient forests.
So wait a minute, this reminds me of something that I learned, which was also a mind-blowing thing, but I never verified it, right? And that was that, it was about coal. And the statement was, there's different, there's some petroleum products that form in the oceans. And there's some, when I say not petroleum, but I don't know what you call oil, gas, fossil fuels, right?
Yeah.
And they're like, when it comes to coal, when the forest material fell to the floor, a tree died, leaves fell. So it kind of sat there and built up. And so I always try to imagine, if that was real, what did that forest floor look like? And then also, it made me think about these coal seams. They have a thickness to it. So does that tell you the story? So tell me what you know about that.
So I've been thinking about coal for a long time.
Okay.
And the ticket is that, you know what a swamp is technically?
Man, I was born in New Orleans.
Okay.
Trees and water.
There we go.
Go.
It's a forest that's wet.
Yeah.
And when a tree falls over in the water, it's protected from being ground up by organisms because it's underwater. It's low oxygen situation. And so the tree sits there, and then it gets more trees will pile up on it. And that's how you accumulate layers of unrotted trees. Because if you let a tree on a forest floor, the termites will go at it, and it'll turn back into carbon dioxide.
Yeah.
And it's gone. As you walk around in the forest, where are all the trees that fell over? They've all gone back up into the air as carbon dioxide. But having a swamp means that that's not happening, and your trees are getting preserved. If you have a swamp that accumulates over time, you'll get a coal seam. And
so you got to be in D world.
You got to be in D world,
and
you got to be in a swamp, to make a coal. And even then, we don't really understand coal formation that well, because there's two major time periods of coal formation in planet Earth history. There's one called the Carboniferous, which is sort of like the 350 million year time range, and then there's one that happened during the end of the Cretaceous period and into the Paleogene, the Paleocene and Eocene, so like 100 million to about 50 or 40 million years old. Those are the two big times when there's lots of coal on the planet. And you say, what's going on the planet that's burying lots of trees in a way that they don't rot away, and we get these huge coal seams. And the really thick coal seams are in that second phase, and there are places in Wyoming where the coal can be 80 or 100 feet thick.
Wow.
So
that meant that there was trees dying, and it built up to at least that thickness before it got buried and turned into coal.
And when you bury it, it's probably going to squish down because of the weight. And it's tough. So, 100-foot coal might have been a 300-foot thick pile of dead trees.
Wow.
And of course, burning that is where we get the electricity for this country.
That's one thing that interests me, is that we power our societies on life.
We call it fossil sunlight, right?
Fossil sunlight,
because it's basically photosynthesis 60 million years ago.
So speaking of which, one place I hear about North America all the time, and I was like, what makes that? Is Burgess Shale. Why? First off, what makes shale, and why is that so fossil rich?
This is so random because yesterday,
No.
I went, and I'm the director of the National Museum, and it's one of our most famous collections, is the Burgess Shale collection. In 13 years, I'd never gone and looked at the actual Burgess Shale collection itself. And I went there yesterday.
Wow.
This is true. This is like,
hey man,
I mean, timing is good.
We're connected.
So I've been to the Burgess Shale in British Columbia and looked at it, and it's an amazing site. It's Cambrian in age, so it's like 505 million years, I think, is the date.
I thought it was in America, but it's in
Canada.
It's in Canada.
Yeah, it's in Alberta. No, British Columbia.
British Columbia.
And it's a place that was in the seafloor. And the way you make a shale is made out of mud. When mud sinks to the bottom, and the particles in mud are clay particles, which are platy. And when you squish them, the plates flatten out, so you get what's called a fissile, or very layered material. That's shale. Shale is fissile or splittable.
Are the layers created by some seasonality?
No, they're just layers. They're just that if you imagine if you have these plate-like crystals and you squish them, they become flat. So the rock's always going to split on plains.
Right.
And that's a shale. And you can have shale from lakes or from the bottom of the ocean. Anywhere you're putting mud down, where mud sinks and still water. And in the Burgess Shale was this very unusual situation where there looked like an underwater slump where a whole bunch of mud slid down the bottom of the seafloor and buried a Cambrian ecosystem on the seafloor.
Like in a single event?
It seems like it. Yeah.
Oh, wow.
It's like a slump that kind of came in.
Yeah.
And there are layers of the muds, and you split these, and it's a black shale. It's like black rock. You split it, and on it are these flattened fossils of all these seafloor creatures. And the key thing about this is that, remember, you have to kill it. To fossilize it, you have to kill it and bury it.
Yeah.
And there are certain times when you do the killing with the burying. It's like a landslide kills and buries at the same time.
Right.
Zero chance of rotting away.
Right.
Boom.
Yeah.
Death and burial.
Death and burial.
And that's what happened. And so here, instead of having just the shells of the organisms, you actually see their tentacles and all their soft parts.
Oh, wow.
And this site was discovered in 1909 by a guy named Charles Doolittle Walcott, guy that had my job.
1909? Oh, no way.
Yeah.
At the Smithsonian?
Yeah, he was a Smithsonian guy. And he found this site, and the site is full of all these little creatures that no one had ever seen before, because no one had ever found an underwater landslide that killed and buried things in fine-grade mud. Wow. And there are all these really cool, weird things. And people have been finding fossils of that age for many years.
Yeah. So how big of an area are we talking?
About the size of the studio.
That's it?
Yeah, it's like the size of a big room. It's on the face of a big mountain range, but it's just one quarry where they've been digging. That's just one quarry.
Man, and so for all these decades, it's even though it's so small, it's still yielding lots of fossils.
Well, those layers going to the side of the mountain, there's fossils there forever.
Oh, geez.
I mean, lots of fossil sites, once you find it, you can go back to the candy machine again because the fossils are there. They're there. And so these slabs, you should come to the museum. I'll show the slabs to you. It will blow your mind.
Yeah.
But they are exquisite. They're little things. I mean, there's an animal called Anomalocaris, which means, I think, anomalous body or something like that. And they got up to about this long, which is like 3 or 4 feet long, which is big because most of the animals of this time period are a few inches long or even smaller.
I see.
And so the Burgess Shale is famous because it's a window into a well-preserved ecosystem that was flash frozen in a moment. And so we have a name for those kinds of things. We call them Lagerstätten. They're just loads of life, basically. And the Burgess Shale is the most famous one, and it was a Smithsonian one. And it is old enough that it tells us a story about the very beginning, and it really tells us how much we don't know. Because you see all these things. Yeah. Every bit of new information just paints a picture of like, oh yeah, now you know even less than you thought you knew.
Right. Yeah. So what you just said reminds me of a particular place where there is always a lot of life. And so, and those are coral reefs. So are there like, fossil just banks of ancient coral reef that just preserves life from, well, first off, I don't know when corals came about. So I'm kind of making an assumption built in there. But, do you have records of ancient coral reefs in the fossil record?
Absolutely. I mean, most emphatically, yes, because coral reefs are like structures.
But to keep the fish and plants?
We have and remember that you can have reefs that are made of other things besides corals.
Right.
But,
is that right?
That's true. So the first corals do go way back. They're corals way back into the Cambrian and Ordovician time period.
Yeah.
But there have been many different kinds of reefs through geologic time. So reefs are made of clams. Reefs are made of bryozoans.
What are bryozoans?
Bryozoans are a very primitive kind of animal that's it's a specific group of animals that have just the little pores, and they're very simple animals. They're like almost like sponges in their simplicity.
Oh, I see.
Right.
Yeah.
So some of them have.
So they're rooted. They're fixed.
Yeah, they can be on stems. They can glue onto things, but they're one type of marine organism that's still alive today. They're still bryozoans.
Because clams tend to occur in clusters as well. So it's that whole idea of clustering and affixing yourself to the bottom.
Exactly.
Okay,
and there are many, many, many different known fossil reefs because the organisms are making calcium carbonate or aragonite shells, and so they're basically fossilizing themselves, if you want to think about it that way.
That's one way to think about it.
And if you go to Miami, all of southern Florida is sitting on top of fossil coral reefs.
Oh,
the whole state of Florida has got coral reef fossils underneath it. Anywhere you go, you dig a hole.
Except the sinkholes.
Well, the sinkholes are holes in the coral reefs.
Why would that exist?
Look, I was just in Florida 3 months ago, and I had the best sinkhole experience.
That may be the first time that sentence has ever been uttered on planet Earth, because sinkhole experiences are typically tragic.
Yeah, well, now we're going to talk about sinkholes in Florida. All right.
Oh, man.
So the bedrock of most of Florida is limestone that's about 35 million years old.
Wow.
So it was deposited at the bottom of the sea, and there's a thick layer of limestone. And
what forms limestone?
Limestone are fossil reefs.
Oh, okay.
It can be lots of different things, but in Florida, they're fossil reefs. They're coral heads and just what you're talking about.
Right. So why is the word lime in there?
Because it's calcium carbonate, and when you bake calcium carbonate, you get lime, which is used to make concrete, right? And so it's a lime instead of an old English word for this
calcium carbonate,
right? And we use, and so limestone
Yeah.
is calcium carbonate.
Yeah.
And so it forms in ocean situations. Can also form in freshwater, it turns out. But in ocean situations, organisms build these reefs, or just layers of microorganisms that make limestone, like the cliffs of Dover, for instance.
Oh, yeah.
Are a sort of non-reef version of the reefs. But Florida has these reef ones, and you can go to the outcrops anywhere in Florida, and you'll see the coral sticking right out of the rock. I mean, it's like, there it is. It does take
This 35 million year old.
Yeah, takes zero imagination to see it. You're looking at the reef. And
Man, I used to live in Florida. I don't ever remember seeing that. So
you don't look at the ground enough, man. You're looking at the stars too much.
Yeah, I'm looking up.
So I went to Florida because I'm working on this fossil atlas of the United States, and I had heard that Florida had great fossils. And I went to University of Florida, Gainesville, where they have a great museum. And I went out with to a limestone quarry where they're quarrying limestone to make concrete and all this stuff.
Yeah.
And we first stopped at piles of the ground up limestone, and I was looking around. I found a beautiful fossil crab, like a fossil stone crab that was like that big, and lots of chunks of snails and clams, all the kind of things you see living around a reef. But then, here's the kicker. That reef was 34 million years ago. Over time, the Earth goes up and down depending on different things, where the continents are. So, like,
You mean the surface goes up and down?
The surface goes up and down. And the sea level is also going up and down. So if you live near the coast, either the sea level can go up and flood the land, or the land can go up and drain the sea, or both happen over time quite a bit. So the limestone of the 34 million year old limestone from Florida, which used to be under the sea, is now, above the sea.
Yeah.
It's maybe 30 or 40 or 100 feet above the sea. Limestone is dissolved by rainwater, right? Because the rainwater's got a little bit of dissolved carbon dioxide in it, which makes it carbonic acid. So raindrops got carbonic acid, it hits the limestone and it dissolves a little bit. So limestone forms caves.
Yeah.
That's where you find all the big caves, like Mammoth Cave in Kentucky, or Carlsbad Cavern in New Mexico.
Wait a minute. So Mammoth Cave is an old reef?
Yes. In Kentucky.
Dude.
Yes. Now you're getting it. You're with me on this one. So you have this landscape now that the rain is making holes, and these caves can get huge. You've seen Mammoth Cave.
Oh yeah, I've been in a few caves. I haven't been in Mammoth. Yeah.
All of those caves are formed by uplifted ancient
God. Now
limestone.
that you mention it, I was in this island in the South Pacific, in the Cook Islands, Mangaya, and it's a coral island.
Yeah,
and
of course.
Full of caves.
Exactly.
Yeah.
Right.
Yeah.
So, but think about marine limestone that's been uplifted. Think about the best analogy, back to food, is Swiss cheese.
Swiss cheese.
It's a block of cheese with holes in it, all of it, right? So now what a sinkhole is when you put some weight on the top of a part of the sinkhole. Because when you lift it up, limestone is formed, these holes in there, they often fill up with groundwater. So it's like a Swiss cheese that's full of liquid.
And that gives it support as well?
Support. But there's a little, so the top of the sinkhole is there, and you park your car on it. And your car weighs enough to crack the hole, and suddenly the whole thing collapses in on itself, and you have a round lake.
And that's the thing, is they're circular. That's
because they're round holes, and they become round lakes. So now you have this thing that's there, and it's a lake that's got steep walls on it because you've collapsed in the side. And if you're a turtle or an alligator, you find your way in there, and they fill up with turtles and alligators. You're living happily in there. If you're an animal walking by and you go for a drink in the water, or you fall in, you can't get out because of the secret walls. So it become a trap. Now, over time, dust and stuff fills it up, and the sinkhole fills up with mud and bodies of all the animals that got buried there. And northern Florida has got, we went to this one limestone quarry, and you could see where they're cutting the wall, you could see cross sections of infilled sinkholes full of fossil mastodons and rhinoceroses and giant ground sloths and manatees and alligators and turtles. And so I'm like, this is the coolest thing I've ever seen.
Right. So it's a big cylinder.
It's a cylinder full of skeletons.
Jeez.
And so, and the museum is chock-a-block full of skeletons, all of them younger than the age of the limestone, 34 million years, all the way up to the Ice Age, 2 million years ago.
Wow.
And we went digging. We went to this other place called Montbrook, and you give you a little knife to dig with. And I dug myself on. First, I found a beautiful fossil turtle. with a skull intact. And then
So do you get to keep this stuff? Or?
No, it goes to the museum there.
Oh, okay.
Like whenever I go, I'm always like, some museum I'm working for. Usually my museum, but I'm always like, this cool fossil.
But is there, like, how does that work? Is there a regulation around that?
Sure.
Like, okay.
If you own the property, you own the fossils.
Got it.
Which means that which is a good argument to buy property. You own a lot of fossils, right? So, this is a piece of property that's owned by a private citizen who is letting the University of Florida dig there. And they've been digging for 10 years. They have, from this one little top of a little sinkhole, extracted something like, I don't know, 100 different rhinoceroses. And when I was there, I dug on to a rhinoceros.
Wow.
So I tell you, I left Florida a changed person because I've been going down to Florida a lot looking at fossils and things, but I didn't really realize the Swiss cheese thing. And there are thousands of those sinkholes, and they're all full of amazing fossils. And as a result, Florida has one of the best fossil records of early mammals in the country. If you want a fossil mammal between the ages of 34 million and now, Florida and Nebraska are your two top places.
I remember you saying something about Earth's memory.
Yeah.
Well,
the fossils are the memories of our planet.
Yeah.
And the rocks are the pages on which those memories are written. So anytime I see layered rocks, because sedimentary rocks are layered, wherever I'm in the world, I see sedimentary rocks. My first question is, how old are those rocks? And then, are they marine rocks or rocks that were deposited on land? That tells me what kind of fossil to look for.
Well, let me ask you a question. So there are certain intuitions you get that, as a professional, that seem impossible before you become a professional.
Right.
For example, looking at the periodic table, it looks like a million different elements. But then, once I started working in material science and things, I got to know a lot of those elements personally, right?
Yep.
Same with the starry sky. It's only 6,000 stars you can see with the naked eye, but it seems like it's a million. But once you start studying it, you get them, you know them by name, basically. I understand that in different geological layers, there are fossils that occur at specific times.
Yep.
So do you have the ability, because you're a professional in this, you're looking at a sedimentary layer like, oh, I see this fossil is this age. Can you do that? Is that a thing?
Yeah.
just off the top of the head?
Oh, yeah.
Oh, wow. Yeah.
I could do it when I was 13 years old.
No way, dude.
I mean,
oh, man.
Because, there are certain kinds of fossils that are common and known.
Trilobites.
Yeah. And trilobites, the first trilobite shows up at 542 million, and the last trilobite's gone by 252 million. So they were around for about 250 million years.
Yeah, that's
They're marine animals, and they are different ones. There's literally hundreds, I think thousands of kinds of trilobites. Oh, wow. But the common ones are quite recognizable. So you could flash me a trilobite, and I'd say, that one's from New York State, and it's Devonian.
Right.
That one's from Oklahoma, because they preserve different ways too.
Wow.
And so the trilobites and ammonites are the other ones, the coiled shell guys.
Yeah.
Trilobites and ammonites.
Tentacles sticking out.
Yeah. Both of those are sort of like the poster children, invertebrate fossils that are poster children for extinction, because they're both extinct. Trilobites went extinct at the Permian-Triassic boundary. Ammonites went extinct at the Cretaceous-Paleogene boundary.
Got it.
And they're both exquisite things, and you can find them, and they come in all sizes. Like the biggest trilobite is like this long.
Yeah.
The biggest ammonite's like 9 feet in diameter.
Wow.
But both of them have lots of little tiny ones too, and so you can, and they have hundreds of species.
Yeah, wow.
So you can slice time very finely with these.
Jeez. What about this thing I heard about Teen Rex?
Oh, that was awesome.
What? Tell me that story.
Oh, yeah. This is the best. This is maybe the best story ever, because it's so surprising. So this guy, Tyler Leeson, I met him when he was 12 years old, and he lived in this little town in North Dakota.
Yeah.
And he was a very curious kid. We love curious kids. And I was there digging with my team. I'd been going there for a long time. I'd been going there for at least 15 years before I met him, I think. And I was in my early 30s. He was 12. I said, come dig with us. He dug with us and stuff. Eventually, he went and got a PhD, became a invertebrate paleontologist. He's a turtle expert. Wow. And he works at the Denver Museum where I used to work at. Wow. So, it's great. He's like my intern turned good kind of thing. Yeah. But his family still lives in that little town where all the fossils are. And his high school friend had 2 sons and a daughter, and the 2 sons who are like 9 and 11, like, we want to be like Tyler. We want to find dinosaurs.
Yeah.
And they live out there.
What 9, 11-year-old doesn't, right?
Right. So they live out there, and they went on this hill that was close to their house. They called up Tyler and said, hey, we think we found a dinosaur. So Tyler's like, well, we'll come look at it. And I was with Tyler. Tyler and I went to look at it, and we get up to the top of the hill, these 2 9-year-old, 11-year-old kids. And sure enough, it was part of a knee bone. There was 2 leg bones attached. But different dinosaurs have different...
So paint the picture for me. So this is looking at a cliffside and a flat on the ground?
No, so you know what Badlands are? They're sort of these rounded, melting rock kind of hills.
Yeah.
It was a rounded hill, and at the very top. These are right at the very top. So it was like this tabletop.
Yeah.
And there was a chunk of a leg like this and another chunk of a leg. It looked like the knee. And different kinds of dinosaurs have different bone textures. So like a Triceratops versus an Admonosaurus versus a Tyrannosaurus Rex.
So that's like the pattern in the grain that you see?
It's like the bone, and you could tell it was bone, and but the T-Rexes have a kind of a shine to them. It's hard to describe. And I looked at it, and Tyler looked at it. We looked at each other like these kids found a T-Rex.
Wow. So you're like, wait a minute.
But we didn't we weren't sure.
That's the mind blowing thing. You know, when you talk about the how you get information, quite often, like you said, all you have is a tooth, and you know all you have is a piece of a pinky bone, or something like that. But the idea that you can look at just a piece of bone and know the entire animal.
It's just years of experience, right? If you look at hundreds and hundreds of parts, pretty soon you can say, oh, that's the left femur of an alligator. I mean, it just, especially if it's common stuff, right?
Yeah, they're that unique one from the other. Like, are there ones that? I want you to get back to the T-Rex story, but just the fact that you just went by that like it's an everyday thing, man. You can't. Oh, I see the surface of a bone. It's a Triceratops.
Well, I mean, this is the thing. Like, you become, especially if you focus on a certain time period and a certain formation, you get to know it really well. And people are like, how do you know that? It's like, well, I looked at, I don't know, thousands of them or whatever, and it's it's like you recognize the Hershey bar. You know, it's
I'll tell you one of the things that we used to do in Mississippi as a kid, because we did so much manual labor. Yeah. Somebody could hold up a wrench, and everybody, any young boy, right? Yeah. You knew what 9/16, 5/8.
Perfect.
Right? Yeah.
Same example. It's just that. It's just familiarity.
Yeah.
Right?
Just familiarity.
And so it's like, and you look at wrenches, I look at turtle parts.
Right. Yeah.
So, but we were like, I was like, it looks like T-Rex. Tyler's like, it looks like. So we're looking at each other, going, what do you think? I'm like, yeah, that's what I think too. So we, and just coincidentally, this is a crazy coincidence. A couple of weeks before, this company was making an IMAX film about T-Rex, and they'd called up Tyler and said, hey, do you know anybody who's excavating a T-Rex? And Tyler's like, no, I don't. But these kids have found a dinosaur. It's probably not a T-Rex, but we'll call you if I think it is. So after that, Tyler called him and said, hey, we actually do think it's a T-Rex. So they said, don't dig anything. We're going to come with the IMAX camera. So they came with the IMAX camera, and the 2 little kids and Tyler were there, and they start scraping away next to the bones. And within 20 minutes appears a T-Rex tooth. Right there. It's like, it was a T-Rex. So then that was great, because now there's this great story of like my interns found this T-Rex.
Your grandchildren.
Yeah, my grand interns.
Their grand interns. Yeah.
So
grandturns.
So then they got a big team up there to chip around. And what you do is you sort of dig around a site, and you kind of expose where the bones are, and you dig around and you trench down around all sides, and then you cover the whole thing with plaster, a pair of soaked burlap strips, and you build like a plaster jacket around it. And on a big block, and this block was about a 6,000 or 7,000 pound block, then you tunnel underneath it, and you run some steel beams under that, and you keep chipping away and adding more plaster and burlap and more steel beams or wood beams
to reinforce it.
So you end up having this giant thing, which is now free from the rock below, because you've chipped all the rocks and the beams, and it weighs 6,000 pounds. You got to figure out how to get it off the top of the hill.
Jeez.
And sometimes you can build a road, you can drag it down or whatever. In this case, it's like, this is a huge thing. So what they did was they got a helicopter, like a big Black Hawk helicopter.
Wow.
We rented that because it was
rented a Black Hawk helicopter.
Yeah. It cost a lot.
So you put that in your grant application. Yeah. We anticipate.
This is where donors come in.
Okay,
a donor rented the helicopter.
Yeah, thank you.
And then I wasn't there when this happened. This has happened after, like I left after they started digging. They tied a cable to the back side of the thing and over the top, and ran the cable down the hill to a car, and they used the car pulling the cable to tip the block up or turn it upside down, so it flipped it into a helicopter net.
Oh, wow.
Okay, so it was in the helicopter net, and then they brought the helicopter, clipped it up, lifted it up on a big thing, and put it on a flatbed truck.
Yeah.
They drove it to Denver.
Yeah.
And put it on display in the museum and started shipping. Now remember, they've turned it upside down. So the original bones, which were on the top, now are on the bottom. Oh. So there's nothing at all in view looking down at the top.
Yeah.
And they started chipping away at the top to see what was there.
Yeah.
And they found what is the most amazing fossil I've ever seen. And I have seen a world of fossils. But as they chipped out, what came into view was the entire face of a Tyrannosaurus Rex, the lower jaw with all the teeth in it, the upper jaw with all the teeth in it. It was like mouth agape.
Wow.
And adjacent to it was a 7-foot-long palm frond with the whole palm leaf there.
Wow.
So here's it looks like the T-Rex is basically a squished head on the side.
Yeah.
It looks like he's eating the palm frond. Of course, he was just buried next to the palm frond. But, and the block is about the size of 4 of these tables. Ooh. So here's a 7-foot-long palm frond and the whole face of a T-Rex found by this 9-year-old kid, 11-year-old kid, and then there was another 11-year-old who was with them when they found it. So
if I Google this, can I get a picture?
Yeah, I can show it to you right now.
Well, it's not going to work for the camera.
All right, we'll send you a picture, put it on there. But you will see an unambiguous palm frond next to an unambiguous Tyrannosaurus Rex face.
Wow.
It is the most beautiful fossil.
And so you can go to the museum and see this? Anybody?
It's in Denver. That was in Denver, the Denver Museum, yeah.
Okay.
You can go see it. It's on public display right now as they're chipping it around. And they have a problem because the palm frond is so beautiful. They want to dig under where the palm frond is. They don't want to destroy the palm frond, so they're trying to figure out what to do. But that's the Teen Rex.
So you have had the ability to see Earth through time. Mm-hmm. And there's been a lot of change, right? You talked about ice coming and going, continents moving. And so right now we're again in a time of a lot of change. There's this rapid advancement of technology and science, as we mentioned, but also, there's climate change happening. There are the ring of fire. The continents are still moving. One question I want to ask you really quickly, though, do you have future Earth, how the continents are going to move, how the atmosphere is going to evolve, and how granular is it? Are you looking at it on million-year time scales, 1,000-year time scales, 100-year time scales? Like, how does your knowledge of the past and seeing that past movie inform the future, and what do you see coming?
There's things that we can predict, things we can't predict.
Yeah.
At the scale of climate, that's an important one because we now have some pretty good predictability, and it's really tailored to how much CO2 we continue to emit. And you can see from CO2 itself as preserved in the ice cores, which go back as far as 800,000 years, or in the fossil marine calcium forams, the plankton in the sea bottom, which goes back 200 million years, or marine organisms preserved on land, which go back 500 million years. You can actually build a climate record for the last almost 500 million years.
Wow.
And the team at the Natural History Museum did that and published the first ever climate curve for the last 485 million years back in September.
No way.
Yeah,
wow,
in science.
Wow, wow.
So you should check it out. Yeah. It's an amazing record because what it shows you very clearly is that more than half of the last 500 million years, the planet has had no polar ice caps. And
so it tends warm.
Yeah, it tends warm. And when it means it tends warm, it means that the poles are forested. So if we can think about what climate is doing right now, it's warming as a direct result of human activity.
Well, let me ask you a question. What kind of makes sense to me? If you have warmer temperatures, that sounds like you'd have more evaporation and more precipitation, which would then dissolve, would rain the carbon dioxide out of the atmosphere, which would then cool it back off. Is that a real thing, or am I just making that up?
Well, I think that what we see from that curve is that there are bounds to the maximum and minimum temperatures. It's like, there were times before the Cambrian, so like 600 and 700 million years ago, we had a thing called snowball Earth, where the entire Earth got covered by ice.
Yeah.
That hasn't happened since we have large life forms. And the arrival of forests and a lot of other organisms that are cycling carbon seems to have kept the planet inside of a range of temperatures.
And so what is that range?
So the range gets quite a bit higher than it is now. Like the mean annual temperature of planet Earth right now is about 57 degrees Fahrenheit.
Okay.
Right? That's if you average the whole thing over the year.
Yeah.
It's gone in the Cretaceous time when the dinosaurs died, it's gone as high as in the 90s.
Really?
Yeah. That's what this curve shows.
Wow, that's like over a 30-degree swing.
Fahrenheit. Exactly. So
they have air conditioning. Like
they had no air conditioning. But they also didn't die. Like this is the thing, is like the planet has had these cool, cold periods. Yeah. It's sort of like there's cool, cold, and warm, hot. And the hot periods are quite a bit warmer than they are now, and the cold periods are cooler than it is now.
So what would you call the current period? A warm period?
I call it a cool period.
We're cool.
Yeah, because cold would have had the ice sheets on Boston and Chicago and Seattle. Warm, you start to melt the ice caps. Hot, they're gone, and you have subtropical forests at polar latitudes. So that's kind of our range. And we now, for the last 2.5 million years, we've been in a cool, cold cycle. Cool, cold, cool, cold. Many times in the last 2.5 million years, cool, cold. And now we appear to be going cool, warm.
Okay. Is that because of humans, or is that?
It's directly because of humans.
I see.
That we've left, because the cool, cold cycle was a Milankovitch cycle kind of thing.
Yeah.
And now what we've done is we've titrated the atmosphere with excess CO2.
Yeah.
And we've turned around that. Because like in the famous study by Charles Keeling, who was measuring CO2 on the top of Mauna Loa in Hawaii since 1957. When he started measuring, it was 300 parts per million CO2.
When was that?
In 1957.
57, yeah.
So, and I know this because I was born in 1960. So he basically started measuring the CO2 the year my mom and dad met each other.
Okay.
And here I am.
Yeah.
And right now, it went from 315. Right now, it's 430 parts per million.
Okay.
So the CO2 concentration in the atmosphere has gone from 315 to 430.
So that's like a 33% increase, roughly, a 35% increase. Yeah.
In my lifetime.
Wow.
So
we don't see that in the past on those timescales?
Well, not on those timescales. So what we're doing is humanity has become a geologic force or an atmospheric force.
Yeah.
And that's what's happening. So we're at a point where we get to choose what we do next. Like we can just say, do we want to just do the experiment, run the experiment, and destabilize the cryosphere?
Well, let's say we don't.
Yep.
Okay. What has the record shown the impact on life has been when you go from cold, cool, warm, hot?
Yeah, so when you go to those temperatures, what you end up doing is you take away the ice.
Yep.
So if you melt all the ice, you're going to get a couple 100 feet of sea level rise, because Antarctica and Greenland.
Yeah.
So the sea level change is one thing.
Yeah.
Second thing is you're going to have migrate. Organisms will migrate to the north as they're being chased.
Right.
And also new habitat opens up.
Life moves poleward.
Poleward, yeah. So you get forests in the poles. The equator becomes pretty hot, and it would be difficult. We're looking at areas where a little bit more warmth, it becomes difficult to be outside and do agriculture outside in the equatorial regions, because you just can't shed your heat.
So everything becomes Phoenix.
Yeah, well, no, exactly.
The equator becomes Phoenix.
Yeah. And that has an impact. It also decreases the polar to equatorial air currents and ocean currents.
It decreases them.
It decreases
so
them.
You get less mixing.
Yeah, because you have, right now we have a big gradient from the very cold, the frigid polar regions, and the very warm tropical. So there's something that's driving currents, is that temperature difference. And you're basically decreasing the temperature difference.
I see.
In a warm world, what happens is that the poles warm, or let's just say they are less cold, much more than the equator warms. So the temperature gradient flattens out.
Right, yeah.
And so you have less gradient from pole to equator.
A hot, stagnant world.
Exactly, rather than in a hot, cold, dynamic world.
Right.
And that's kind of the trend. And how fast that happens is still kind of unknown, but it's pretty clear that it's happening.
And it seems to be surprising us, because from what I understand, the changes are occurring faster than anticipated.
Let's think of all the things you've heard of recently, like atmospheric rivers, or like the Gulf Stream doing that meandering thing that dumps a lot of snow. All these things are like, once you see them, like, oh yeah, we predicted this. It's like, you didn't predict it. You predicted instability, and instability is manifesting itself in the present
You don't know exactly what that instability is going to look like.
Yeah, but I think the key point that came from this big paper that was published in the 485 million year curve is that the driver is CO2.
All right, man. So everything I'm hearing, working at the museum, you sit in this place where you get to see many different areas of science, and all of these have been rapidly just increasing knowledge, increasing data. So I imagine that you have some sort of like holistic view now of science, where it's at, where humanity is going, where the planet is going. How do you summarize your view from your perch in your position?
I think the key points are this. One, I think science is an amazing human endeavor, and it's because we are curious primates that we pay attention to things. And what science has done is we do experiments, we observe things, we share the knowledge, we move it forward. So knowledge grows as a collective human endeavor. Yeah. So you and I are both scientists, but we know what we know, and we don't know what we don't know. But you put all 10 million scientists in the world together, and all the discoveries that are being made every week by all those 10 million scientists, humanity is getting smarter very fast. Yeah. And we're understanding this. And there are a lot of things we don't know, a lot of basic things of the planet we don't know. But the planet is so incredibly interesting, whether it's the couple million to 10 million species of living things, or whether it's the geology, whether it's the meteorology, or the patterns of how it all works together. And one attribute of there being so many scientists is that most scientists are focused on one very specific aspect of the scientific knowledge base. Right. And I think the great privilege I have as being the director of the National Museum of Natural History, the world's largest natural history museum, is I get a bird's eye view of a whole bunch of the scientific world. And it is just endlessly fascinating, overwhelming, thrilling, and I just am thankful every day for the ability to see what I see, and experience what I experience.
I still see the same joy that and curiosity. I was that kid too, in a different. For me it was relativity and Einstein. For you it was looking down and finding things. And I imagine, man, I still have it. It looks like you still have it.
Oh yeah.
You're just, it's like coming to you. You're like feeding from a fire hose of scientific knowledge, and you just have this perch where you're like in the Marvel comics, they had the Watchers, right? You could just look at all knowledge going around in the universe. You're like Earth's equivalent to that.
Well, that's an awesome statement.
Right? Yeah.
I definitely don't want to sleep ever.
Oh, man. Yeah. Well, you get to synthesize all this stuff in your sleep. And does that ever lead to like, I see it now? Right.
Well, you get these steps, and often it'll be somebody makes a different discovery, which makes your observations fit into place. Yeah. There's a lot of things where you're confused about, like, what goes on here? Like the Bennu thing was, I learned so much from the guys doing the Bennu project. I didn't do any of that work, but I was proximal to them when they were doing the work, and I could ask them questions. So I love interviewing a scientist and understanding, because it is hard to understand all of it. I mean, no one can do it. There was a book called The Last Man Who Knew Everything.
Right. And I love that.
That's like 1850. And he, back when there was 25 scientists or whatever. But now it's, we're in this collective endeavor, and it's been so fun talking to you, because your knowledge set is quite different from mine. And
man, you're blowing my mind.
We could talk for another 12 hours, no problem. No problem.
And we will, now that I got you. Now that I got you, man. Yeah, this has been amazing, Kirk. I'm so happy that I've had the opportunity to chat with you. This is, and you will be seeing me showing up at your doorstep.
Perfect. I'm looking forward to it, Hakeem.
Love it.
Thank you, man.
Thank you.